Thank you for everyone for joining us here today. We are going to go through what is UT, what does it do, a little basics of what it is, and then we'll talk about the new machine that we have. So my name is Josh Wilson. I'm a technical sales manager for Allan Edwards. I do everything from drawings to discussing technical details with customers and you name it. So I'd like to introduce David Futch, let him talk about himself a little bit here.
Yeah, welcome everyone. Appreciate it, Josh. My name is David Futch. I'm the Director of Materials Engineering here at ADV Integrity. We're a small consulting company outside of Houston. I primarily specialize in all things metallurgical, including welding, failure analysis, whatnot, and also heavy on the pipeline repair, which brings me here to talk to you guys today through Allan Edwards.
So we're going to talk about what is ultrasonic testing, or UT. How does it work? We're going to discuss our phased array automated machine, the advantages of UT, the bottom line for what UT means to use the customer, main takeaways, implications for pipeline industry, and then we'll have a Q&A session. So as we're going through this, if at the very end of the Q&A, if you have questions, feel free to type them up in the chat, and we'll get to them there at the end. David, I'll let you run with it there.
Yeah, perfect. So I think it's important here to start a little bit high level, right? So what is UT, right? You see UT flashed up on the screen. It's important to start a little bit high level and understand what exactly that is. I think that sets the stage nicely for what Josh will get into here in a bit. So at the very basic, right, what is UT ultrasonic testing? It's a form of NDE, or non-destructive examination. If you think about the world of NDE, right, there's many different types. Anything from visual, you use your eyes, maybe a mirror and a light, something like that, to gain a better perspective, right? UT allows you to do that, though, through the use of ultrasonic sound, right? Ultrasonic sound that bounces in and out of the material to detect different flaws, laminations, things that could be surface or slightly subsurface or throughout the wall. You think about other types of NDE, you're probably familiar with those. UT is just sort of an adaptation of that. You'd probably use it anytime you're trying to find wall loss due to corrosion, or you're probably using it to get the wall thickness maybe before you make a weld. But in this case, we're talking about UT, at least from the product sense of how you can use UT in order to gain a better perspective. So it can detect surface and subsurface flaws, and it allows for that ultrasonic frequency propagating through the material, right? So you have some sort of transducer, and it kicks in, and it measures some sort of time and strength to get the feature or get the ultrasonic sound back out. Interpretation of that done by some software package or someone that's an expert in the field, then can help characterize what exactly that feature is. You're seeing some dip, some change in time, and then you're able to interpret that as, oh, it looks like wall loss, or it looks like a lamination, something thereof. So we go to the next here. How does it work, right? And we kind of walk through that. You've got some sort of transducer. In this case, on the top of that gray little schematic, some sort of transducer there, that's the kicking sound into the material. And you can imagine, as you're looking at the right-hand side of that same image, if that transducer hits something, in this case, that little arced shaped flaw, the signal isn't able to penetrate through it, right? So you get some sort of reflection back out of the steel, and it's captured by this transducer. So if you think about what that would look like, you get two different peak patterns shown there on the right, and then someone could then interpret that. So if you think about where this could great to be used, you're able to detect things you visually can't see with the naked eye, right? So you can't see it, and therefore you may not know it's there. So employing something such as UT allows you to see subsurface, maybe mid-wall, allows you to gain a better perspective of whatever that material is that you're looking at. In this case, being a steel sleeve.
So that brings us into, what is Allan Edwards' phased array UT machine, and what does it do differently than what's out there? So, phased array is a method of UT. It is really, it's a lot more advanced. It gives you a lot more resolution. So in this graph, you can see a conventional UT probe that may put out a single signal or multiple. They can usually go up to 4, 6, 8 signals. Ours is more of a bar shape, and it does produce 64 beams. So it is much more advanced in that method or in that way. We have 64 beams rather than a single, which gives us about a 10 times more accuracy. Phased array allows for the collection of the encoded data. So what that really means is we can see a lot more information than what you would see out of conventional. On the collection screen that the machine has, you're going to be able to see exactly, it does a full C scan. So you're going to see what flaws they have, what size they are, and it's going to record all that data for not only a report that's fully traceable, verifiable, or complete, which is called a TVC report in the industry, but you're going to be able to record that data and retrieve it later on as well. Advantages of UT. So what the UT, as David mentioned, it's detects flaws that would be invisible to the naked eye. It is 10 times more accurate than conventional UT, and I said the other day it's 100% more accurate than not doing any form of UT. So if we look at the still sleeve industry as a whole, the use of NDE is pretty limited. I mean, we look at the tensile reports, we look at MTRs. You may have a mag particle report, but unless it's specifically called out, UT or any other advanced form of NDE is not used in the industry. So this takes that level of inspection and puts it out there for all of our products, and it just gives you the peace of mind and full transparency. So these reports are provided in our standard data package. So not only are you going to get the MTRs and you're going to get tensile test reports, post tensils, post forming tensils, but you're also going to get we do Charpies, and we're going to provide the UT report for every sleeve that we produce. So this is showing a little bit of video of the machine scanning the plate. So it's got a water bath. It does a 10% overlap. This is real speed. So it scans a plate in approximately about 4 minutes. As the machine feeds the plate in, it does edge detection to not only align the C-scan to the plate, but make sure it does UT thicknesses, so it pulls the right calibration for the machine. Off to the side of the scanner, there's the blue line there to the side that has the orange nozzle. That is a air line. So if it finds a flaw, it will go to that flaw, it will dry it, and then it will mark it. So the machine is smart in that regard, being able to not only see the flaws, but then to show where they are.
Okay, so sort of getting into the meat of it here in the summary, right? I think it's a pretty cool piece of technology you saw there. So scanning, getting real-time data, really understanding what that steel itself is. And, if you put yourself, many of y'all are operators, you put yourself in the shoes of, hey, you've got an issue, right? You have something that has to be repaired on a pipeline. You want to be able to pick up the phone, you want to call, and you want to get a quality product. Quality means a lot of things, right? Quality is you get what you pay for, you get the right thing, you get it on time, so on and so forth. But quality also means you're getting a piece of material, in this case, a sleeve, a steel sleeve. You're getting a piece of material that has some sort of integrity bound with it, right? So it is able to, survive the length of time that you need it to survive, and also allows you some comfort if you get out to the field and something's a little bit different. It may allow you to work around it, right? So you think about UT, what could you find? Let's play hypothetical. Maybe you find some laminations in the starting plate. Allan Edwards could reject that and use a different piece. And if you think about another option, maybe they don't know it's there, and you go to cut that sleeve from a 10-footer to a 5-footer, because that's all you need for the repair you're making, and you find that lamination, you attempt to weld it, it causes other issues, and now you're kicking the can down the road. causing more and more issues. So if you're able to get a better quality product, at the end of the day, hopefully that allows you to make a better quality and a quicker, easier repair. Right. So if we think about it, we go out, we buy a sleeve, we want to put it on the pipe. We're making an assumption, and it's a good assumption, not challenging the merit of the assumption, but we're making the assumption that that steel repair sleeve has comparable integrity to the pipeline steel. We're buying a certain thickness, we're buying a certain grade sleeve material that likely matches or is comparable to the pipe steel itself. Right. And we're also then making an assumption that that sleeve we're putting on is an effective long-term repair. And we have tons of data to go to that. Right. It's really not an assumption. It's more of a statement of fact. Lots of data out there. We've been putting sleeves on for years and years. There's lots of test data, some that Allan Edwards has done as well, that shows the long-term ability of those sleeves to perform. Right. But if you think about it, you're getting a piece of plate that's then rolled that has some QA/QC check, maybe when it's leaving the shop to make sure it's the right length and the right bevel and the right this or that. But if you think about it, there's no standard, no proof out there in industry that says you as a sleeve manufacturer has to meet a certain quality standard. There's no product testing once that sleeve is formed. And if you look around the room you're in, right? I mean, everything around you is likely manufactured to some standard. Probably the desk you're sitting at, believe it or not, has some standard it's being manufactured to. But steel sleeves are not, right? Steel sleeves are built and made to the best of the ability of the manufacturer. And so by doing something such as UT, we're able to elevate, you're able to bring more quality to that steel sleeve that's being manufactured. Why exactly does it matter? And we'll go through a couple bullets here. Josh, I'll let you advance, right? So you think about you're building a pipeline, right? You probably do some sort of extensive NDE on that line pipe that you just went out and bought, right? You're building a cross-country line. You're going out, you're buying the best pipe you can find because you're trusting that that's going to give you your 50-year or 100-year design, whatever you've come up with. And you think about the pipe that's in the ditch already that's been there since the 50s. You excavate it and you spend hours collecting NDE data, right? And so if we've done that, we've put our pipe to that level of NDE, that level of scrutiny. And you think about that steel sleeve that you're then putting around it, it essentially becomes an extension of that pipeline. So I think you could then make the argument, well, why aren't we doing that for the steel sleeves themselves? Right? There's no NDE required. Sure, granted, there's NDE after you make the weld on your hot ends or your long seams. You come back and do mag particle. Some may do other methods, but mag particle pretty common there. But there's nothing to say, did the sleeve I put on, did it meet something of an integrable or some sort of criteria? And so if you think about why it matters, right? If you know that that steel is of the right thickness, free of laminations, gouging, other internal flaws, you're able to get a much higher quality steel sleeve product. So food for thought. And I think this quote actually summarizes it quite nicely. You know, like I kind of said, if you're going out, you're buying pipe, you're subjecting it to the most complete ND that's out there, some sort of UT, maybe some X-ray, this or that. If we become accustomed to inspecting the carrier pipe to that rigor, why aren't we doing the same rigor or the standard of care to the sleeve material? Right? You think about it, you put a steel sleeve on and yesterday, you probably expect that steel sleeve to be there for the next 30, 40, 50, 60 years. Who knows? Right? There's some lines that are 1920s built that probably have sleeves on it that are approaching 50, 60 years old. At that time, maybe no one was thinking about it, but if you're able to know that that steel sleeve has the same quality of care of the pipeline, you're able to maybe sleep better at night. You're able to understand that that steel sleeve truly does have the integrity of the surrounding carrier pipe.
So the main takeaway in all of this is that Allan Edwards performs 100% phased array UT on all of our steel. We do that as a standard, no exceptions. You know, what are the implications for the pipeline industry? So the quality of the repair product matches the inspection standard of the carrier pipe, as David's mentioned. I mean, there is no standard out there, so we've created our own standard. And our standard, our product, regardless of what the baseline inspection requirements are for the operator, we across the board, it's 100% UT, no questions. It's definitely more stringent than regulatory challenges because there are no regulatory standards for steel sleeves at all. So it's definitely more stringent. It's repeatable, reliable, and traceable record of the steel plate quality. So just assuming that the MTR and your tensile tool tests and even Sharpies that's been done on the steel itself, this is just taking it one more level up from that and making sure that these invisible flaws that are not visible to the naked eye, that they're found before the product actually gets out the door and on the pipeline. So with phased array UT, you get what you inspect, not what you expect. That's a very telling, as David mentioned, I mean, the expectation is that the repair product is going to be there as long or longer than the pipe. But there's really nothing, I mean, there's nothing that really guarantees that. And, doing phased array and everything doesn't guarantee that it's going to be there, for a million years, but it's definitely better than doing nothing at all in the industry whatsoever. All right, we're in the Q&A time. I'm going to go through the questions that have been posed in the chat, and we can discuss each one. The first question here back, will these reports be provided with the sleeve order? The answer is yes. They will be provided. We've been providing them all year long. We did install our new machine here about a month ago. We were doing it with a robot before, still phased array and 100% UT. But now we're doing it with our automated machine. And it is of the plate, not the rolled steel. What measurement is 10 times more accurate, and how was this determined? Is this sizing variance, etc.? We have a level 3 UT who reviews all reports and has been in charge of making sure that the machine is adequate for what we're doing and making sure it meets the criteria for the ASTM spec that calls out the criterion. So 10 times more accurate is from a conventional UT probe to R64 probe or 64 element probe. That's what is technically 10 times more accurate. And that's from a single beam. If it was an 8 beam, let's say if a conventional probe had 8 beams instead of 1, it wouldn't be 10 times more accurate. Let's see. The next question was, any thought for future scanning of the as rolled sleeves? We're open to anything. I mean, we're definitely, we're pushing the envelope as far as what sleeve manufacturers are out there doing currently. So, we're just going to be continuously pushing the boundaries and making sure that, we're providing the best product out there. So that could definitely be, an option down the road for sure. Does the UT only measure thickness and laminations, or also capable to detect cracks in plate thickness direction? Yes, it is scanning thickness, laminations, cracks, any kind of voids, you name it. It will detect pretty much any defect, subsurface or on the surface. The next question is, repair sleeves would likely have weak points at the welds. Should PAUT welds be performed in addition to the common 12-hour MPI? That's more of an industry question, more of an installation. David, do you have any thoughts on that?
Yeah, so that comes down to the operator, right? So code tells you that you have to inspect your sleeves for features that may form due to the heat and the cooling of the weld metal, right? Typically, the limiting feature is a toe crack, right? So toe crack being the outside of the weld at the carrier pipe, because that's the flaw that could go through wall and then to leak out of the containment of the sleeve. So that's why the common 12-hour, 24-hour, whatever the operator comes up with. The use of PAUT then is up to the operator. I know some do it, but it would be up to the operator. And I would argue if you're going that route, you need to establish acceptance criteria before you go that route. Having the acceptance criteria in hand would certainly help justify what exactly you're seeing when you do that scan.
The next question was, what is your acceptance rejection criteria for the flat plate before rolled into sleeves? So the specification is ASTM A578 to acceptance criteria A with an S1, which is 100% scan. And so that is the standard. When did AE start to deploy such PAUT to the sleeve manufacturing? Was the next question. We started that January 1 of this year. Every sleeve that has left our facility this calendar year has had phased array UT done on the raw steel before manufacturing. We did at our 75th anniversary open house here last month. We did introduce our new fully automated stationary machine that we showed the video of, but we were doing it previously with a robot. Next question is, what happens when you find issues with the plate? So the machine itself, like I said, it will, if it finds a rejectable defect, it will go to the area on the plate. It will dry it because it uses water as a couplant. So from the video, you can see the water coming out of the head. So it will dry that water. It'll spray a spot on the plate where the scan found the rejectable area. That rejected plate then goes to a holding area for further examination. And it'll be either, if we have enough usable plate, there's a possibility we can utilize part of it, or we reject the full plate. So that's our procedure there. Next question: do you believe phased array UT before rolling the sleeve improves the odds of avoiding axial cracking in the sleeve post rolling? We have found that since we have started scanning the plate, we don't see any visual cracking afterwards, which we have seen in the past after the rolling. So we definitely do believe that it does improve the odds of avoiding it. David, do you have anything else to add on that one?
So the sleeve obviously goes through some sort of bending form as it's being rolled. And so if you have a lamination or some sort of feature that can be a kickoff point or a starting point for something happening when the outside of the sleeve goes into tension during the rolling process, then identifying that ahead of time could certainly save the reject of that sleeve if something happened while rolling. So I agree it would increase the odds. I don't know if there's a percentage you could imply on it though.
The next comment is we're currently using Flexoform UT to scan for anomalies in pipe. Maybe consider something like this for the rolled sleeves. Great suggestion. Thank you, sir. And then the next one is, you mean ASNT, correct? So yeah, the ASNT is for the qualifications of our level 3, but the specification for the actual inspection on rolled plate or on steel plate is ASTM A578. That is the specification for it. All right. Well, David, do you have anything else you want to add?
No, I appreciate the opportunity to come on and talk about this. I think it's exciting to see a manufacturer, step out and do something above industry standard, industry normal. So it's exciting from my point of view to see that, and hopefully you guys on the call here felt a bit of that excitement too, or get to see a bit of the whereabouts and Allan Edwards adding that technology.
Yeah, and we, if anyone has, any further questions, feel free to send them to us. We're an open book. If anyone wants to come tour our shop, see the machine in action, we're open and welcome anyone that wants to come. That's, we're very proud of it, and it's something that we're trying to do to, like I said, push the envelope and push the industry forward and produce a better product for everyone. So. Hopefully this has been, informational, and we appreciate everyone's time, and hope everyone has a great day.